All right. You can all see my screen. Thanks again. Thanks very much for having me. So this is definitely not exactly a C++ talk. This is a little bit of sort of more meta and thinking about the role of software and how we approach, doing software as professionals. I really like this talk. I've been giving this a few times, although remarkably, I don't think there are actually public recordings of it. So hopefully you'll enjoy it. And this talk means a lot to me because it actually is derived from the pitch that I gave to my VP a couple years ago that got the original approval for the book. So this one means a lot. So I'll start with sort of the big question. What's the secret? When I do outreach like this, or I give conference talks afterwards, people ask, what's the secret? Why does Google seem good at software? We aren't always, that's part of the secret, but we seem that way maybe. And actually at CPPCon a few years ago, one of the early ones, I had a pitch and I said, for the low price of $5 million, I will sell you a tool that will enable you to keep your code base happy and healthy forever and all of your developers working productively. And if everyone in the audience chips in, I'll even grant you exclusive access to it so you can resell it however you like. And for $5 million, this seems like an amazing deal, right? Like everyone that is pitching into that stands to make a massive pile of money and I get to go retire to a beach somewhere. Win-win. And yet, I don't see anybody reaching for their checkbook. Even if this was a serious business pitch, everyone understands really intuitively, really instinctively, that such a thing can't actually exist. So why is that? And the hint goes all the way back to the 1970s and Fred Brooks and the Mythical Man Month essays, right? There is no silver bullet. There is no one tool or language or engineering practice that is going to provide us with a 10x productivity boost. Instead, it's a continuous slow march as we refine technology and processes and ecosystem and understanding. And we see that with the SRE books, right? It's not just one thing that takes you from the bad old days of spotty uptime and low reliability and early days internet and gives you big system like Google style reliability and performance. Instead, you need a lot of little things. There's changes that are necessary in culture, right? Google is a big proponent of the blame-free post-mortem. You need changes in technology. If you're gonna run reliable services in production, you have to have monitoring for that. You need to know if it is up. You need to know if the system is healthy. And most importantly, I think, SRE introduced us to the idea that we are framing the problem wrong, right? It isn't about having 100% uptime. It is about formulating our error budgets, our SLAs, our SLOs, and using the budget of how much downtime do we have left to us as a resource. And so taking a cue from that thinking, from the writings and the SRE books and the thinking on how do we do reliability, I'd like to present what I think are the core tenets, the way that we frame problems at Google that make software engineering different and effective. These are the main themes and theses of the Flamingo book. And the first is a question of time. How is time going to affect all of our products? And it's, I think, very well captured in the question, what is the expected lifespan of this code? And it's important to realize that there's roughly 6 orders of magnitude of reasonable answer to this question, right? You can reasonably say, I have a thing that I'm working on, it's going to last for a couple minutes. And it is also perfectly reasonable to say, I have a thing that I'm working on, and it's going to last for decades. But yet we don't discuss this question, and I think it's critical. Very often, when a novice is learning a program, the lifespan of the resulting code is measured in hours or days. Those snippets are not touched again after their initial production. In some colleges and universities, we might have a project course or a hands-on thesis. For most students, that is literally the only time that code that they work on is going to live longer than a month or so. And that short life expectancy doesn't change necessarily when you graduate and you enter into the industry. A large amount of the software industry is focused on startups or apps, things that have a notoriously short expected lifespan, usually between 1 and 3 years, depending on what you look at. Most of the effort in a situation like that is focused by necessity on keeping the business alive. A startup may not live long enough to reap the benefits of any investment in long-term sustainability, right? You don't want to build for 20 years if you're going to go bankrupt next week, right? You have more pressing concerns. And then, of course, even in large companies, there are all of the projects that are just thrown away after a couple of years. But by counterexample, successful industry projects and open source projects may have an effectively unbounded lifespan. We can't reasonably predict an endpoint for the Linux kernel or the Apache web server or the C++ standard library, right? In most Google projects, we can't predict when we no longer need to upgrade our dependencies, our language versions. These long-lived projects have a different feel to them than programming assignments or startup development. Another example, another way to look at it. On the short end of the spectrum, if I'm hacking on a Python script to process some logs or something, and a new version of my operating system comes out, should I stop what I'm doing and make sure that my script works on the new operating system? And I would say nobody is going to say yes to that, right? That's kind of wild. But on the other end of the spectrum, if I have code that was written at Google 20 years ago, and we have not been able to update it to a current version of GCC or a current version of Linux, that's an unambiguous signal that something is deeply wrong. And together, even just these two data points suggest that there's a kind of scary transition in here somewhere. Somewhere around the 5 or maybe 10-year mark, we start getting into, yeah, we really have to upgrade this. And unfortunately, the cost of paying down everything that is built up in those first years is particularly rotten. Doing your first upgrade hurts. And it hurts largely for 3 reasons, right? 1, you're performing a task that hasn't been done to this project before. Hiram's law applies, and therefore you have everything that has ever accreted in a Hiram's law sense is going to be in your way, is going to make doing an upgrade hard. Your organization is doing it without expertise or experience, right? You don't have engineers that have been through this before. You're kind of making it up as you go. And most of the time, you're going to be doing a larger than usual jump. You're jumping from C++ 98 to C++ 17 instead of just C++ 14 to C++ 17, right? And all of those things together are hard individually, and I think they multiply together to make this a really, really hard thing. And unfortunately, this is also the experience range of most developers, right? You sort of work with code up until the point that it starts getting really important to do that, and then maybe you do it one time. But after doing it that one time, or even just giving up partway through because it's very hard, it seems reasonable for your organization to overestimate the cost of doing the next one. And you just decide never again, and you commit to always throwing everything out and rewriting it. But getting through this, not only this first time, but getting to the point that you can reliably stay current going forward is a big part of what I call sustainability for software. And sustainability is the goal. For the expected lifespan of your code, you need to be able to change all of the things that you ought to change safely. And for particularly long-lived projects, making that transition to sustainability can be awfully challenging. Many projects just can't do it. And many developers have never actually worked on a sustainable project that recognized that it was going to be around for long enough that it had to go through all of this upgrade regularly. So when Google comes, or we have conference talks or whatever, and we say, this is how we do things and why, some chunk of that just sounds to a lot of people like utter nonsense, right? Why do you have all of these processes in place? Why do you worry so much? Why do you have all these steps and safeties, right? It's, in many people's experience, not necessary. It's never going to pay off. But I'm here to tell you, if you're working on a long-lived, sustainable system, then that is playing a different game, one that has different best practices. It's more than a short-lived programming project. And I also happen to think that a lot of these practices do actually pay off in the short term and will serve you very well as you grow. So software engineering, I assert, is not merely programming. It is the art of making a program resilient to change over time. So in the same way that SRE pushes people to realize that error budgets actually define the reliability problem, software engineering is about realizing the production of software is not the goal. Solving problems and keeping those solutions working as long as is necessary is the goal. And this is the first lens in our, say, theses, our principles of software engineering. Be mindful of time. If you're worried, if you get to the point that you understand the impact of time on your software and you're successfully making things last, then you probably need to start worrying about growth. And when change over time leads to growth, the thing that you need to look for is where do you start to fail? And in particular, I'm very interested here in the human resources of this. Right? There is the question, as you grow in age, are the things that your software relies upon scalable? Right? And this could be hardware or software resources. But I'm much more interested in, are the things that you must do that require human effort, are those also scalable? Because in the end, software engineering differs from programming by both having a time dimensionality and a far, far larger teamwork dimensionality. So when your project doubles in scope after doing, say, that first upgrade, and you have to perform that upgrade a second time, is it going to be twice as labor intensive or 4 times because you have so much more code to work with? Or can you make it cheaper? And I'm just going to assert that everything that your organization relies upon to produce and maintain code, all of your processes need to be scalable in terms of general cost and resource consumption, but especially scalable in terms of human input. And time and scale come together in interesting ways. I'll talk a little bit about what Google sort of learned about deprecations and churn quite a few years ago now. So we can look at deprecation, right? A traditional deprecation approach is you mark the old thing deprecated, introduce a new one, and just call it good, right? You ignore the existence of the old thing. And this, over time, is not hard to see how it fails. As new versions are introduced, if you don't have a forcing function that actually pushes unmotivated legacy users off of the old thing, then we wind up with an ever-increasing amount of maintenance for purely legacy systems. And sometimes that maintenance is actually pretty negligible, right? It doesn't actually hurt you to have an extra function that your maintenance never actually touches, right? But sometimes that maintenance can actually be actively costly. Storage systems and things come up pretty regularly in the Google context. If we were supporting the storage systems from 10 years ago in production still, that's kind of a large sunk legacy cost, right? It may cost us something to force people off of it, but over enough time, it's going to be less than the ongoing legacy maintenance. Another thing that is pretty common is you mark the old thing deprecated, introduce the new one, and tell everyone that they have to update their code by some date, and you delete the old one on that date. And this, I would argue, also doesn't scale, right? Because as a code base or as an ecosystem expands, projects have an ever-growing set of dependencies below them. If every dependence, like if you look at graph growth algorithms, right, you probably have something like the square root of n dependencies, where n is the number of nodes. And as your dependency network increases, that is still kind of growing in an unpleasant way. If every dependency underneath you has the right to say, every one of our users must move from the old thing to the new thing by 2020, then you're increasingly forcing all of your developers to run just to stay in place, or they fall behind. And even worse, every individual on a team that gets stuck with, okay, I got tasked with doing the upgrade this week, has to individually learn all of the details of that upgrade. And for a large organization or for an ecosystem, right, you're going to pay that learning cost over and over again, and then you're going to throw it away, right? Because it's one developer on one team that is doing one upgrade, They're going to do it one time without knowing what they're doing, and then they're going to be done. And the worst part of all of this is that most projects that you depend on aren't leaves, or rather, most projects that depend on you aren't leaves. Most projects that depend on the C++ standard have dependencies on top of them as well. And this means that the threat of, I'm going to delete this, is disproportionate, especially in a continuous development or trunk-based development or monorepo sort of world. Right? You aren't just breaking the build of the project that didn't obey your threat. You're breaking everyone that is downstream of them. Right? The analog that I like to go with is you might threaten your kids with, hey, Timmy, if you don't put away the dishes, I'm going to blow up the city. Right? This might get the dishes to be put away, but if not, then either your threat is false and you don't blow up the city, or you're primarily harming bystanders that had nothing to do with the great I didn't put away the dishes debacle, right? This is not good policy. And finally, some deprecations are handled just by resorting to heroics, and everyone knows heroics don't scale. So instead, what we try to suggest is something like the churn rule. Right? The majority of the cost of any change needs to be paid by the team that is making the change, that is forcing the change. There needs to be a published and reviewed transition plan. And this deeply constrains the designs for whatever the new thing is, but it puts all of your incentive structures into scalable places. And buried in there is a very important point, which is, practically speaking, policies like this scale better specifically because knowledge and expertise within an organization have superlinear effects, right? They scale very nicely. It's very important. That is, making the team that triggers the change into specialists that understand how to disseminate that change, how to enact that change, is a much, much cheaper outcome in a world where, especially in a world where all of your users are visible to you or you can automate things. We only pay the ramp-up cost a couple times, and then expertise makes things quicker and cheaper, right? There are economies of scale to be had when you apply expertise to problems like this. So I'll just assert that in a successful organization, in an efficient organization, everything that must be done repeatedly has to consume sublinear resources, especially sublinear human resources. Also, of course, codebase, you need to look at codebase size, scaling, and build test resources. Growth rates on all of these things tend to be slow and steady, and monitoring is a good idea. When it comes down to it, you have to be aware of scale. Don't fear it, but you do need to respect it. Right? It is a sign of success. It's a good problem to have. Some examples about scale. For another glimpse into how does this scale, consider version control policies and merging. I ran a Twitter poll a while back that suggested that about 1 in 4 SWEs software engineers, have had a regularly scheduled meeting to discuss the merge schedule. Right? And this is the idea that we have some number of teams that are all working on their features on individual long-lived dev branches, and we need to coordinate and decide who gets to merge in what order. Right? It's not rare to encounter development shops that have this. A team might be off developing on a branch for a month, they finish, they merge, and then you find out that the release has become unstable. And of course, we've all seen this, right? Big merges can be costly. And faced with that realization that big merges can be costly or risky, you have two options. You can control that cost and lock it down, or you can figure out how to just make it cheap, right? You practice, you reduce the cost, you make it common. And depending on the situation, one or the other might be good, but for version control the cost path is bad, and the research shows that, right? This is why, as an industry, we're moving towards trunk-based development models. The published research backs me up on this. No long-lived dev branches, no choices in where to commit, no choices of what version internally to be depending upon. And I think that this version control example is a perfect microcosm of what I mean by watch out for scaling problems. Companies that I was involved with before Google absolutely relied on this sort of merge strategy meeting that had different teams and different contractors working on long-lived dev branches. At one point, we even had to hire an additional full-time content management engineer to handle the load for merge and retest operations. Because when we got to 200 engineers, the one guy that had been doing it before couldn't keep up anymore. And that second engineer, of course, didn't double the throughput for merge operations. They had communication and coordination overhead between the two of them, just as would be predicted in every engineering text for the last 50 years. Google internally has a couple hundred times that many full-time engineers, but nobody is responsible for the merge. It just works, right? It isn't that our engineers are that much better. It's that we spotted that this policy doesn't scale. We found something that required fewer decisions and less communication and less coordination. Another quick example of time and scale playing together is, I think, shifting left. In the past decade or so, this idea, this terminology has emerged in DevOps methodology especially. Shifting left makes things cheaper. The earlier in the software workflow that you can catch bugs, the cheaper that they are. And I see this as a direct result of your thinking about your software ecosystem in terms of time and scale. Originally, this was phrased in terms of shift left on security. And as an industry, it was increasingly common to think about security tacked on to the very end of the software process. But as it turns out, it's real expensive when you have software bugs that are only discovered after release. Software that has already been released is constrained and hard to change. Security bugs in the wild have legitimate real-world consequences, potentially up to the loss of human life. Catching those same bugs before that software is released into the wild is vastly cheaper. Users aren't depending on the feature. We don't have the same legal liabilities. We can fix it and try again. We pay for testing, maybe canary costs, but that's still much, much cheaper than this going wrong. It would still be cheaper beyond that if we caught it in code review. At the moment in code review, the developer responsible knows what they were trying to do. They've already got the details fresh in their head. Languages like Rust are prioritizing make it hard to even express the risky concepts, which pushes this focus on security all the way back into the development step. The same basic principle, shifting left, applies to bugs of all forms, right? If a bug shows up in Canary, that's cheaper than if it was released. If we catch it pre-submit, we know exactly what broke. If we catch it during development, it may not even register as a hurdle during the developer's work. And I think this ties very nicely to time and scale. It's a time issue. Imagine building two houses. One construction company has alarms in place that detect when something was done in an unsafe fashion and sounds an alarm instantly. The other company has detection that is just as good, but the alarms only go off on move-in day. Which house would you buy? Or, for that matter, which house would you rather build, right? One of those is going to be a much, much higher quality product. But I think it's also a scale issue. If we handle time perfectly by moving to a world where we have just push on green continuous deployment and we can submit a change and instantly see it in production, so long as the test pass, then it's still cheaper to find bugs earlier in the process because you don't have to worry about, was this caused by me or someone else or the interaction of our two changes together, right? The more variables that you can take out of the equation, the cheaper it's going to be. So scale is the second important thing when considering tools and policies and practices for software engineering, or really anything, but it's particularly acute here. So considering these two ideas of time, how things are going to change, and scale, how your system, how your development practices especially are going to work as you grow, all that's left is make good choices, make evidence-based decisions. If we understand that change must be possible, if we are explicit about the lifetime for the software that we're producing, and we understand the scaling goals of our organization and our engineering process, all that's left is to focus on making good decisions. People often say that everything in engineering is about evaluating trade-offs, and I find that that is definitely true in software. The important thing is to make data-driven or at least evidence-driven decisions, accounting for the realities and the requirements of time and scale. You need to aim for sustainability, right? Your code, for the lifespan of your code, must be capable of change. Otherwise, you are placing a sort of high stakes bet that change is never necessary. And as you're aiming for sustainability, you're going to make thousands of small decisions. But if they're done with that clear goal in mind, for whatever the expected lifespan of your project looks like, then you're going to be in a better place, right? Change must be possible. No superlinear scaling, especially for humans, right? Care for your humans, be a good team member. And critically, because time and scale both have a tendency to change things, you need to reevaluate from time to time. Context changes, and the reasons and the evidence that go into any given decision are going to change over time. A decision from last year might have been right at the time, but it may become wrong next year. It's reasonable to summarize all of this as make logical trade-offs, and in many respects, I think it shouldn't need to be said. Of course, you want to make logical choices if you want good outcomes. But this is less about a surprising insight and more about focusing on the important philosophy of the thing. Within Google, there's a strong distaste for because I said so, right? Inherent in all of this is the idea that there needs to be a reason for everything. Just because, or because I said so, or because everyone else does it this way, are places where very bad decisions lurk. And so when I'm asked, what's the secret? I don't have one answer. I have many answers, and at minimum, these three, right? Software engineering is more than programming. It's about time, right? And if you are not thinking about the long term, if you're not thinking about the lifespan of your code, then you're just programming. And that's useful in a lot of cases, but it's not usually the answer in the highest functioning aspects in the tech industry. You need to be mindful of scale. Superlinear scaling is bad for processes that you're going to have to do over and over again. But expertise and specialists have a tendency to counteract that. So choose wisely. And make good decisions. Make evidence-based decisions. Try not to rely on because I said so. And remember that the evidence is going to change over time, so you need to reevaluate as necessary. The Flamingo book, the software engineering at Google book, this is basically chapter 1 of that. And then it goes on to sort of discuss a lot of the cultural aspects, the how to be a good team member, how to be a leader, and then policies and processes, the sort of squishy things that you write down, and then the tools and tech that we think actually makes all of this work. Remember, going forward, it's programming if clever is a compliment, but it's software engineering if clever is an accusation. And that's what I've got for you today.
My first question is basically, how do you create the atmosphere? You've mentioned no blaming, etc. So how do you create the atmosphere for research and people will be able to put their ego aside and be able to correct their mistakes? Everyone making mistakes and
right.
It's important to be able.
Yeah, and to be clear, I think it's more than just in research. Like my team's, the Abseil team reports to me. Like we maintain the most fundamental common library infrastructure for everything at Google. You can't hire people that can do that job perfectly with no mistakes, right? And when they make a mistake, it's going to be visible to thousands, more than 10,000 engineers in all likelihood, right? And so that's challenging, right? That said, what we focus on a lot is the long term, right? It has to be a matter of time. And thinking about it in terms of you have one team where if you make a mistake, you're going to get fired. Or you have one team where if you make a mistake, we are going to learn from it and make it harder to make that mistake again. And, praise you and support you for, oh, you found something interesting. Like we didn't know, I didn't know that weakness, that vulnerability, that flaw in the system existed. And which of those two teams is going to succeed over the long term, right? Over a couple months, over years, right? The team that learns from their mistakes instead of hides it and shifts the blame is clearly going to outperform. One of the ways that my teams for the last few years have tried to tackle the culture behind that. We have during our weekly stand-up, there's a ritual that we do of kudos and the monkey. And so people go around listing kudos, like gratitude, thanks, to people that have either, hit a milestone, had a nice achievement, helped out, like gave a good presentation, like jumped in to help you solve a bug, like any of those things. Because there's a wealth of psychological and sociological research on the importance of gratitude, right? Being a good person and saying thanks and being open to people helping and acknowledging their help turns out to bond your team together real strongly, right? And so just making a habit of making that normal is a really good thing. And then in terms of making mistakes, the second part of the ritual is the monkey. So I actually have stuffed monkeys with little t-shirts on them that says whoops, that I have printed up for all of my teams. And you can nominate yourself for the monkey by saying, I believe that I have made the biggest mistake this week. And then you tell an interesting story, right? And it's all in good fun, right? Sometimes we're formal enough about it that we're like, yes, you win the monkey, and then you get to put the monkey on your desk. But like, whatever. Mostly it's about, one, admitting it, two, telling the story, and three, like the team collectively listening to those stories and learning like, oh, okay, there's a thing, like how are we going to stop that, right? And I don't want to say that like there's no penalty to making a mistake, right? There's no penalty to making novel mistakes, right? If you refuse to learn, if you intentionally, obstinately just keep messing up the same thing, yeah, we're going to have a talk with you, of course. Like we need you to be a professional and to learn, right? But the vast majority of the time, the stuff that people are actually going to mess up is wild, right? And very understandable. And so we go to great lengths to try to normalize and encourage and celebrate, like, oh, okay, now we have the opportunity to learn an interesting thing. Yeah, and the cohesiveness and culture that has emerged partly from this. I'm sure that there's more to it than that, but that has been a big part of it, I think.
Right. So you're basically saying the team is embracing there, and I think that's great.
Yeah.
Thank you. Gior, I have a question. Gior, would you like to speak? Or do you want us to?
Yeah, sure. I might have written quite a lot. I'll try to shorten it down.
Sure.
We are working on software that will probably exist for many, many years to come. And a lot of us, like you can say, the more senior engineers that work on the software are aware of things that need to be done to make sure that the software is sustainable. Some places in the system have done it, some places haven't. And we often want to make sure that the places that have not ensured that the software is sustainable, we want to make changes over time to make it sustainable. Mm-hmm. But it gets to the point that management doesn't quite play well with us, I guess you can say that. And there is often a lot of things that a lot of time needed to put to make the management understand that it needs to be done, or right. Even put it as part of the work. Is there like something, I don't know, a way to convey the message, something that you can recommend? I guess, I don't know.
Right.
I don't know.
No, no, yeah. I understand, and I wish that I had a single pithy, easy answer to that. Like, we suffer from issues with technical debt ourselves. There is always, the conflicting pressure of we need to ship new features versus we need to like clean things up. What I'm increasingly fond of, if you're having those conversations with management, a lot of the time, especially if you have non-technical management, it's very important to get them to realize that software ages, like bit rot is a thing. And some of the time, even if you made the best decisions you could have at the time, you've learned more since then, or product requirements have changed since then, and like you haven't really, bundled all of that in. If non-technical management is, under the mindset that all code is equal and everything is fine and it will just like keep humming along forever, then that's going to be a problem. If you can get them to realize that it's a little bit more like, I don't know, machinery, like a car, maybe, like you need to change the oil, you need to change the filters, you need to do some maintenance on stuff, and things do break down from time to time. The other aspect of it is in organizations where management really doesn't encourage or endorse or allow time to be spent on those sorts of like clean up after yourself and maintenance tasks. A line of reasoning that I think is scary and hopefully compelling is, if we have never changed this code, we may not know how to do it when it matters, and there are security bugs, right? Like, if you do not know how to change this, right? If no one has actually modified this system in years, right? Then when the next Spectre, Meltdown, Heartbleed, whatever comes around, right? That is distinctly increasing the lag time between your ability, like between vulnerability publication and the time that you can fix it, right? And when you start threatening there's going to be a liability issue in here, then they will stop like harassing you. But in a more like healthy sense, I think the most important points to make are really, we need a certain amount of time to like clean up our workspace, and the code base is your workspace, right? You can't be expected to be super productive like on exactly the thing that needs to be done all of the time. You need a little bit of time to tidy up after yourself, like now that you've finished construction. So if they're not, like, you need to bundle in some time there. But you also need to make sure that especially your junior engineers, don't think that everything that is bad is equivalently bad, right? Because I think most of the bad taste for like code health and cleanup and refactoring work comes from people that don't know the difference between, oh, the linter complained, or, oh, this warning flag went off, and it doesn't matter, versus this is the thing that is actually slowing us down because the design is bad, right? And so you need some ability, whether it's from more senior engineers or team vote, whatever, like, what are the things that are actually hurting us and slowing us down? Not just, I don't like it, but like the stuff that matters is the stuff that you need to target most.
Thank you very much.
May I ask a question?
Yeah.
Go ahead.
This had earlier huge mistakes that developers sometimes do. How do you document these mistakes?
So if it actually causes, like if it rises to a certain level, then we tend to, like there are there's a repository of postmortems. Like, this was a problem. Like, you go through and sort of write up a timeline of what happened and when, like, where did you get lucky, like what actually like went into resolving it, what are you going to do to fix it afterwards. And those things are published. A lot of it, if it doesn't rise to that level of severity, is sort of maybe not captured anywhere. And that might be the wrong answer, but I'm sort of not sure. But yeah, it varies, I think, is the best answer I've got.
Okay, and I have another question. There's sometimes the need to create to make superlinear changes. How do you do it, and how do you describe the need to do it?
I might suggest that there are several chapters in the book on that. Yeah, I think there's not short answers to that. Broadly, I think it's an issue of you have to be able to convince management that it's actually impactful. And we have found over and over again that it's necessary to do some of these things. For instance, we, in a very concrete fashion, we had a big project for some time to develop our own hash tables, because the ones in the C++ standard library are very, very slow. And you can't just change the standard library, you have to change all of the code. And so having the infrastructure in place to know how to identify all of the hash tables and change them from one type to another, and do that safely and do that without breaking people's builds and all of those things. There's a lot of policy and tech that goes into that, but the end result is a fairly substantive improvement in CPU and memory results. My friend Matt Kulakundis gave a talk on this in CPPCon. I forget exactly what numbers he quoted in there, but like, we're talking, percentages of fleet performance, which sounds small, but adds up to a lot. So, like, there are many knock-on effects to having the capability of doing that sort of thing.
Okay, thank you.
Yep.
A question regarding internal open source or internal code share between distinct projects. Do you encourage, and if so, how do you manage sharing of code between distinct and in some cases competing projects?
Almost everything inside of Google is one giant monorepo. Like, everything is shared, everything is like trunk-based development. If it's not Chrome or Android are really kind of the big ones, I guess TensorFlow now, then it's primarily developed internally in that same trunk-based repo. So like the C++ repository is 250 million lines of code with maybe 12,000 developers that'll commit something to it every month. Every single project in that repository depends on me, and a bunch of projects that my teams own. Like, the dependency graph is enormous, cross-cutting, etc. And it works fine. It scales. Like, it's a vastly better system. You don't want releases. You don't want like communication overhead. You just want everyone understands what is current, and you add dependencies at trunk. You don't get to fork things. There are no long-lived dev branches, like maybe less than 10. total, the whole organization. You rely on tests. You pay for continuous integration. You run the tests. You have a build system that's not garbage. The chapter on build systems in the book continues to blow my mind. It was the first chapter that an external, one of the non-lead authors wrote that was like, oh my Lord, that's why that works. Like, I had a completely different understanding and experience of build systems before I got to Google. And like, as it turns out, there's a theory there. And if you don't follow the theory, then your build is probably bad. But I have been doing, like, my teams make thousands, tens of thousands of changes a month. I don't remember that it's ever been necessary to make clean. It's just not a thing, right? Like, you never need to. And the reason for that is we have a good build system that understands dependencies and caching and parallelism. And as a result, everything just interacts cleanly. And we have a consistent understanding of what the code base is. And we can run all of the tests, and things get auto rolled back if you commit a change that breaks everybody. And like, it's a different model, but it is definitely the model that, as the chat describes, like, it is the model that is increasingly being found to be much more productive than what we have just thought was stable. And I sort of think of it as a difference between static stability and dynamic stability, if that makes any sense, right? It's one thing to build a thing that can stand stably, and it is quite another thing to build a thing that can dynamically balance. And we are running, and that is a matter of dynamic balance. And it sounds weird and awkward, but so does riding a bicycle.
So if a developer needs a feature or new parameter inside some API in the networking utilities, he just gets in, adds the additional function parameter, it builds, he runs some tests and waits for the nightly build.
There are no nightly builds. It's everything is always current, like current within a minute. Practically speaking, that scenario just doesn't actually happen, because when you have tens of thousands of people that are working on the same infrastructure, like, all of those features have been done forever. It's not important. And the other part of that is we tend to have higher level infrastructure than you would expect. Like, there's not a socket class inside of our code base.
Networking was just an example.
Yeah, I know. But,
you know, somebody needs an additional thing in some utility, and the utility has an owner or no owner.
Yes, yes. Everything has an owner. Some of those are active owners. Basically, my career is based on early, like 2010-ish. We realized that a lot of the oldest, most utility pieces didn't really have active ownership. And I was one of the founding members of the team that was like, okay, we're going to do code reviews and try to make sure that, like, these things are, like, actively owned, and we don't just say yes to everything. We, like, dig into why do you actually need this. We evaluate your designs. We see if it generalizes. We see if there's a cleaner way to do it, all of that stuff. And my whole career is basically downstream from that decision. But yes, in theory, you can submit a patch to be considered by pretty much everything. All of the code is visible, or almost all the code is visible. Yeah.
I have a question. To what extent can you rely only on automatic testing? Is everything covered by ongoing automatic tests, or do you also need, to some extent, manual testing?
I can't say that there's no manual testing, but that's mostly just because Google is so big that, like, there are things that I'm not aware of, I'm sure. But effectively, everything is automatic testing. And there's defense in depth for that. There's continuous, like, there's a strong, solid culture of writing unit tests. at the point that a system is too large for the unit tests to run in a reasonable amount of time or to be reasonably reliable, then you start moving to larger integration tests, maybe things that are spinning up, an isolated database, stuff like that. The integration test frameworks tend to get up to sort of an end-to-end size, at which point they're effectively the same as your canary evaluation. Like, I have cut a release, I would like to know if this would be okay if I put it in production, is basically the same question as your end-to-end integration test, and tends to actually use the same sorts of infrastructure. And then we have formal canary and then monitoring, but it's all actually the spectrum. Like it's all they are highly related. There's a talk I give in a couple months that will probably be recorded and posted and make the rounds on Twitter. But I believe that that spectrum, like from end-to-end monitor, or from production monitoring all the way back to unit tests, there's a philosophical sameness in that's very connected. But the vast majority of it is all very automated, it's very rare for anything to be manual. And it's important that it's not, because going back to like my teams, if we're making changes in the very bottom of like the most critical, most common code, the only way that we can tell if that is safe is by running everyone's tests. The only way that we can run everyone's tests is if there's one button we can push that runs all the tests, right? If every team has a different manual process for doing that, those tests have no value to us. Like, we can't do that. We can't promise to run some manual process from 5,000 different teams. Like, that's not going to work. So instead we force everyone, like, if you're going to have a test, it needs to be triggered here. And that keeps everything sort of on the straight and narrow. Lots more on this in the book.
Anyone else have a question? Okay, kept mine. All right, then I'll go very briefly, because so it's actually a bit broader than the topic of your talk, but I was wondering, how do you approach to designing a new library? And I know it's like a very wide question, but I was wondering, how do you spend a lot of time on design, or is it more of a process that's...
We have a weird scenario, and I don't think that it necessarily generalizes. And it's largely, like I said, the Common Libraries teams only spun up starting 2010. Google was 10 or 15 years old at that point already. Like, we had a lot of like utility stuff laying around already. Like, and it wasn't necessarily like well thought out and deep, but like that was common and existing, and lots of code was written for it, like logging systems and command line flags and file and all of these things, mutexes. And so most of what my team has excelled at has been taking those existing pieces and figuring out like how to improve them in place. And so we are by nature highly constrained by the ways that everyone is already using them. And that is a wholly different beast than the sort of like, I would like to write a new thing. There are some new things, but we almost always have large bodies of existing use case and need to generalize from. Like, if there's fewer than 100, 500 uses of the thing, like we forgot. Like, it's not important. I can't count that low. Like, and so like we're operating in a highly constrained like legacy system setup for the most part. That said, occasionally there are new things when we are discussing how to improve an interface, there's a lot of design. There are a lot of, like, there's a chat channel that I haven't checked on in an hour and a half, and I guarantee that they've had at least 20 messages on some esoteric design question, because they just always do. And one of the nice things is like discussing and iterating on like the design and the principles in design, and trying to generalize and trying to extract wisdom instead of just knowledge. It certainly helps you level up. Like there are deeper truths in all of that, and it's not always obvious. I was having a conversation with someone the other day. Like, it's very nice that our organization has internalized so much stuff, and like nobody has to think about things like your hash operator needs to be operating on the same values that your equality operator is, like, which sounds believable if you haven't heard that before, but like it's just true. Like there's a deep fundamental aspect of design, just as an example. And it's very nice to have a community that has just agreed and absorbed and like continues to push forward. Like, so.
That's really awesome. Allow me to be just a bit cliche and say that a friend of mine talked about, she's an artist, and she gave a talk, and she talked about how creativity is actually something that's created by constraints. So I think that's actually like very cool. The fact that you need to stand up for some constraints that makes your code more. So yeah, that's really awesome. Giora, I have another question.
At what point do you think it's best to go work at Google? I would recommend that you have some experience outside, for a number of reasons. Like Google has its own way of doing a lot of things, and also a lot of things that it just has wild blind spots on. One of the examples that's near and dear to me is because we have this whole mono repo thing, and because everyone just depends on the versionate trunk for everything, we Googlers tend to have really naive understanding of dependency management problems and version skew and like stability issues, because we don't have that. Like, we have taken that whole problem away from everybody, and that's curious, right? And so like there's a lot to be said for working at Google, and you'll advance and learn a lot, and it'll be fascinating, but it is not everything, and it is not representative. So yeah, but I am very glad that I have done it. I have been here for 10 years. It's hard to imagine being anywhere else. And it is still exhausting, because you look at basically anybody else that's working there and you're like, wow, I could not possibly do that job. Boy, do I not deserve to be here. And that's emotionally taxing. So, yeah.
I'm sure it is.
Yeah.
Do you have any more questions? Last chance. Does Rust have less pitfalls than C++?
Yes. I think in many respects, Rust is a lovely language. It does constrain you a little too much. Its compile times are worse than anything modern. The thing that makes me hesitate to say that Rust is the answer is that there's an unfathomable amount of C and C++ code out there, and Rust does not interoperate well. And like, it's a very 1980s approach to imagine that you can just build a whole new thing and it'll be fine and take over the world. Like, legacy, y'all. Like, so.
Right. Hey. Well,
Cool.
being is a good thing.
Yep.
Titus. It was really,
Okay.
really good.
Great. Thank you again for having me. I got to run. So.
Thank you so much,
Cheers all.
Titus. That was fascinating. And I know I'm going to read the book now, so you can count me in. I'm
Nice.
sure many others are greatly interested and curious to read more. So thank you so much. And
Thank you. That
hopefully
was
we have you up
inspiring.
again for another talk later this year. So
It's
let's
possible.